In this quiz, we're going to be looking at periodic trends as well as orbital diagrams and understanding quantum numbers, which show where the different electrons will add within an atom. And so for our first question, we're asking about ionization energy, and we want to know that if we are to subsequently ionize an ion, right, so we take one electron and then we take a second electron, that the second electron is always going to take more energy than the first. Question is this true? And the answer is yes, it is true, that it's always going to take more energy to remove that additional electron. And this is because, we've already removed an electron, so what's changed about the element, which is now an ion? Well, the balance of electrons to protons has only become more positive. So even though there are certain states that cations like to reside in, certain favored ionization states, it's still going to be harder to remove a subsequent electron because the electrons are only going to be more closely associated with the nucleus. So as ionizations continue on, they only get more difficult. And the next question is, how can we use these subsequent ionization energies, which we've already discussed are going to be increasing, to predict the most likely charge for a cation? And here, what we want to think about is, where is there a big jump in ionization energy? So we know that it's going to be always increasing, but if we look at a table of ionization energies, what we'll notice is that there is a place where there is a big jump in ionization energy. And so here's a sample of this table. And what we look at here is that we already know, these elements and the ionization states that they generally tend to prefer. Potassium likes to be +1, calcium likes to be +2, and so on. And what we notice here in red is that this is where the big jump has taken place. We go from about 400 kilojoules per mole to about 3,000. For calcium, as we go from ionization energy 2 to ionization energy 3, we again have about a 5-fold increase in that ionization energy. And so what's happening here? Well, this is removal of a core electron. Remember that potassium has 1 valence electron, calcium has 2, scandium has 3, and therefore it's not that hard, relatively speaking, to remove those valence electrons. But once we're trying to remove a core electron, which is one that is part of that noble gas configuration that's tightly held inside of an atom or an ion, that's when things get really difficult. And the take home here is that only looking at the ionization energy table, we can say, oh, here's a big jump. And if we don't know what the element is, we can determine, therefore, how many valence electrons it must have and possibly identify what the element could be. And this does reflect the periodic table. The key here is understanding successive ionization energies and what a big jump in ionization energy means. All right, let's shift gears a little bit and talk about electron configurations, which are definitely related to what we've been talking about. We want to know the abbreviated electron configuration and orbital diagram for iron 3. This is Fe3+. And for our electron configuration, here we have the following. Iron without an ionization, so just plain old iron, is going to be 4s2 3d6 to show those 8 valence electrons on iron. And remember that when we remove electrons from a transition metal, we're going to want to remove from 4s first. That's because when occupied, the 3d energy level actually drops below that of the 4s energy level, making the 4s electrons easier to remove. And so here's our electron configuration. Orbital diagram. What we don't want here is like a picture of the Bohr model of the atom or something like that. That would be a diagram of an ion, but this is what we're talking about when we say orbital diagram. It's this arrow diagram. And we want to show 4s is empty and 3d has 5 electrons, all of which are spinning in the same direction, either all up or all down. If you picked all down, that would have been absolutely fine as well. Neither state is higher energy than the other, but it is essential that they're all spinning in the same direction, either all up or all down, and that they're not paired. They want to sit in their own orbitals before they pair with another electron. Final question is saying, well, what if we put an electron into this iron 3? What is a specific set of quantum numbers to define this electron and why? And the first thing we need to know is, well, what orbital is this electron going to reside in? And the answer is that, well, we have occupancy in 3D. So the electron should add into 3D, as that is the lowest energy state. And so when some electrons are present, 3d is lower than 4s, so the electron will add there. If you ended up adding one into 4s spinning up, I think that would be a pretty good answer as well, and your answer would be a little bit different, but I think is definitely still on the right track. So just keep that in mind, but these are really the only two correct answers. Is it's going to add spinning with the electrons that already exist in 4s, so it's going to spin in the same direction as the 3d electrons, that's up as this diagram shows, or it's going to pair with one of the electrons in 3d. If we're going to go with 3d, n equals 3, L equals 2, this defines 3d. If we have a different n and L value, it's going to be in a different orbital, different sublevel. And for ML and MS, I've chosen ML equals -2 and MS equals -1/2. Note that for ML, if we're going to add into 3D, we actually have 5 options which represent the 5 different orbitals within this 3D sublevel. And that would be -2, -1, 0, +1, and +2. Those 5 numbers represent the 5 different orbitals, the 5 different spaces, that is, in the 3D sublevel. MS could be +1/2 if we were to represent the other 5 electrons spin down, or somehow had a convention where we were to say, well, this pointing up is -1/2 already. The point is it has to be opposite what we've already established because they're going to pair together, and if it wasn't opposite, they'd all have the same quantum numbers. Keep in mind that even though there are multiple potentially correct answers, if we want to assign quantum numbers to a specific electron, we absolutely must have specific quantum numbers, and knowing that is a really important part of working with quantum numbers and orbital diagrams.